Good morning. Yeah, now you can hear me. Welcome to the IvS seminar. We are again like almost a full house. That's great to see. So the seminar is going to be given by Mariam today. Mariam got her bachelor's in the United States, University of Michigan, I believe. Then she moved to Switzerland for her master's. And then we decided to hire her as a PhD student here at IvS. And she said, like, nope, I like the project, guys, but I don't want your money. I'm going to get my own. So she got FVO. And now she's standing in front of you, ready to present the Marvel project and what she has been doing during her master's. So please, Mariam, the floor is yours.
Hello. Oh, okay. Hi, everybody. So thank you for the wonderful introduction, Andrew. Like he said, I'm going to be talking about my early work and what I am and will be doing with the Marvel arrays. So that will be my title there. So the overview of this talk, there are two sections. The first being the early work, some theoretical background, the methods that I used to carry out the experiments I did, as well as the results I obtained, and a short summary. And then we'll move on to current techniques that I am investigating for the Marvel array, a little bit of an introduction into what Marvel is and what we can use it for, as well as the work I'll be doing in the future on top of the current ongoing work. So starting with my early work, which was done at the Geneva Observatory, and starting as a very brief overview of science. Humans have been looking up at the night sky for millennia, and in those millennia, we've been able to discover a lot of really interesting things about space. One of those interesting phenomena is exoplanets. These are planets that go around stars that are not our sun. And the first exoplanet was discovered by Michel Mayor and Didier Queloz in 1995, actually, so it's a pretty young science. And this is 51 Peg-B, the first discovered exoplanet. You may be already excited that we've discovered exoplanets, but maybe you're wondering how we went about doing that. And so there are a multitude of methods that you can use, but I'm going to be focusing specifically on one for the beginning of the topic, and then a combination of two for the second part of the topic. So how do we find an exoplanet? So observables that we see in space are, well, observable not only in the visible part of the spectrum, which is a small part of the electromagnetic spectrum, but really in a wide range of wavelengths. And observables exhibit a spectrum of these wavelengths that we are able to observe using what we call a spectrograph, which is an instrument that we can use to divide the light, the incoming light, from an observable and record it so that we can look at what it's made of, really what its chemical composition is. And this chemical composition can be seen in these little things we call here called absorption lines, for example, where in the presence of an element or a molecule, we'll see ironically, the absence of that in the spectrum of the observable. And so we can find out the chemical composition, but what else can we learn from the spectrum of a star? Well, we can indirectly observe exoplanets. And so how we do that is that we look at stars, and when we see that there is a gravitational pull exerted on the star, such as there is here, where there's the presence of a second body going around the star. What we actually see is the spectrum of the star and the absorption features within it undergoing what's called a blue shift, or a shift towards shorter wavelengths as the star comes closer towards us in our line of sight, and a red shift, or a shift towards redder wavelengths when the opposite happens and it is moving away from us in our line of sight. And so this is visible in the radial velocity profile of the star, and this could hint at a multitude of objects going around the star, but if the conditions are right, that object will be a planet if it's not too big and not another star. So where are we now with this endeavor of searching for exoplanets using the radial velocity method? So this is just a small chart of all of these exoplanets that have been found within a certain error for the radius and the mass, along with which instruments have been used to discover them. This is specifically looking at smaller mass planets, but as you can see here, there are not very many Earth-like planets that we have discovered to date, and there's even really missing planets in this parameter space too. And so there's quite a lot more that we need to do in terms of looking for smaller and smaller planets, being able to characterize more planets that are either Earth-like or mini Neptune-sized, or super Earth-like. And so for this to succeed in accessing smaller planets and discovering systems maybe more like our own, we have to investigate solutions for every step of the detection process. So focusing on my early work, this is a very oversimplified version of how we acquire a science-ready spectrum. But my focus was specifically in the data collection phase and looking specifically at the calibration frames that we take to observe a spectrum, and specifically, again, flat fielding. And so one of the aims of my master's project, it wasn't the whole project, but this is most relevant to my Marvel work, was to design and produce a low-cost, long-life, continuous white light source that could be used for spectral calibration in the visible wavelength regime. So what is spectral flat fielding? If you're an observer, you probably already know, and if you work with spectra, then you definitely know. But for other people, flat fielding can take on two forms. It could take the form of a spectrum with spectral flat fielding, or it can take the form of like a 2D image, as you see with photometric flat fielding. With spectral flat fielding, what we do is that we take the spectrum of a white continuous light source, and the point of this is that we're trying to correct for the pixel-to-pixel non-uniformity inside of the detector, and we're trying to correct for the systematics that are there. And this is with any detector that you use. And these systematics occur not only in the raw data that you collect of an object like a star, but it's also visible in the flat field, and that's why we use that to correct for it. So here on the left, you'll see a raw flat field spectrum. This is what it looks like if you were just to collect it as it is, and the reason why you see this bump here is because this is the Blaze wavelength of the spectrograph that was used to collect the spectrum, so you have the most efficiency at that wavelength, so you collect the most intensity. But if you were to correct for that, then you would end up getting this really nice, smooth, flat field that is completely flat for the wavelength regime we're interested in. And that is more or less the goal. The goal for the masters was to develop a white light source that would be nice and flat, just like this. So all we're doing is correcting for the systematics of the like stellar spectra, but not over this very small wavelength, over the entire visible regime. So in order to assess whether or not our light source that we were investigating is worth investigating, we also wanted to compare it to what was already on the market. But keeping in mind that the light source we have has to produce a high signal-to-noise ratio, otherwise trying to use it to calibrate your data will actually put more noise into your data, and it's actually counterproductive. It has to be overall uniform in terms of its flux over the desired wavelength range, otherwise it's not good enough to correct your data. And it also has to cover the same target spectrum of wavelengths. This is a little bit more obvious because if it's not covering the visible wavelength regime, then you can't really correct for it. So comparing to other light sources that are already on the market, the laser-driven light source is used quite often. However, it's really quite expensive, despite it having a really broad spectral bandwidth, high output power, high signal-to-noise ratio. But we are looking for low cost. The other option here would be a supercontinuum laser, which also has the same advantages as a laser-driven light source. It's a bit cheaper, but it starts to introduce nonlinear effects like Raman scattering. And again, it's expensive. So again, we're looking for low cost and long life. The closest competitor that we had to what we chose as a white light source was the tungsten halogen lamp. And this has a broad spectral bandwidth. It is inexpensive. It does technically cover the visible wavelength regime. However, you can see that towards the bluer side of the visible wavelength regime, the power density is much lower because the lamp peaks in the near infrared. And so it has a very fixed spectral coverage. And so what we decided to investigate were LEDs. And so the promise of LEDs came that they were a powerful, or they are a powerful light source underexplored in astronomical instrumentation. They have a flexible spectral coverage because you can combine different LEDs in order to get the part of the spectrum that you're interested in. And it ranges completely over like the visible wavelength regime and a little bit on the sides. And the power has a range depending on the package you're buying it in, but it also has an extremely long lifetime, and it's exactly the type of lifetime we're looking for. They also come in a variety of forms depending on the type of application you want, such as surface mount technology, LEDs, flat window, and then indicator lamp. And depending on which application you go for, they can be more or less expensive. And so when comparing the light sources, just taking a laser-driven light source, the tungsten halogen lamp, and an individual LED, if you were to just take the specifications taken from the market in terms of power, and if you were to look at the light emitting area, and this omega is the solid angle or the light emitting cone of each of these, you could see that the average spectral power density of the individual LED is possibly comparable to the laser-driven light source. But the issue here is that if you're trying to combine light from multiple LEDs into one output, you're going to be losing a lot of that light. And so that's where the challenge is. And so the laser-driven light source was the sort of the standard that we were trying to achieve using LEDs. But the challenge really was trying to combine the light from multiple LEDs to achieve that purpose. And so we have that limitation that I mentioned already. It's called étendue, so this is the, I suppose, the phenomenon of when you have light coming out of a light-emitting source, or when you have a source that's trying to receive the light. There's a limited surface area that is emitting that light or receiving it, and there's also a limited cone from which it can emit or receive. And so when we have light from an LED, for example, and it emits light in this very wide radial pattern, and you're trying to get it all into a fiber and couple it, you end up having all of this lost light on the sides. And that's something that we have to contend with. Light can also be lost in between if you have different optical components that you're trying to use to couple that light in, if it's being lost on the sides, for example. And so, yeah, it depends on the acceptance angle of the fiber, it depends on the radial profile of the LEDs, but light can be lost in a multitude of ways before you can actually get it to couple in. So that's a big drawback in optics. And then there's also the spectral bandwidth when it comes to LEDs, another limitation. They have a limited spectral bandwidth compared to other sources, but you can combine them to achieve the type of covered spectral range that you're interested in. So this is less of a drawback in terms of whether or not we can cover the range, more or less, but it is a bit of a drawback, as you'll see later, because we can only fit so many LEDs into our design before we run out of space physically. And so you have to find LEDs that cover as much of a bandwidth as possible that can all fit into one fiber. And so we went through different designs for how to achieve this, how to get multiple LED light into one fiber. The first being the integrating sphere. So the idea of this tool is that you would have a sphere that has a highly reflective surface on the inside, and we would drill multiple holes, or we would call them ports, where we would inject light from different LEDs, and the LED light would undergo multiple reflections before it comes out of here in the fiber. And so I did a lot of theoretical work with that and found out it didn't materialize into something we wanted to follow, so it ended there. But with just one LED and just a limited bandwidth, we just wanted to see how much light would get out on the other end. We found that when we used a 15 millimeter radius integrating sphere, we didn't get very much power density, spectral power density at all when you got out to the other side. And if you were to reduce the size of the integrating sphere, then you would be able to have fewer internal reflections before it reaches the output. And so that's where you see the increase over here in the throughput, but that's not really, it's still not on the order of the laser-driven light source, so this was pretty sad. So we decided to move on and try something else, and this was incorporating a prism instead. And so the idea was you would have different LEDs that would cover the whole spectrum, and you would collimate their light onto a prism or a dispersive medium, and inversely disperse them so that you can converge them using a second lens onto an output fiber. So that's the idea here. However, when all of the math and the ray diagrams and everything was drawn out, unfortunately, it was not feasible because when you follow the white light all the way to the other end, it only left 8 millimeters for 10 or 12 to 13 LEDs. And the 12 to 13 comes from the fact that I was looking through the whole market and the whole internet, and that's the fewest number that I needed to cover the whole spectrum. So we did not have enough room. And so we decided to go with a more dispersive medium than a prism. We decided to go with a grating. And so this became the design that eventually was materialized, as you'll see in the next slide. But the design is that the LED light would be first coupled into an input fiber via a series of ball lenses. So these are some optical components to refract the light in. And then that series of fibers, that light would be injected and hit the first lens, which would collimate the light, onto a transmission diffraction grating, again inversely dispersing the light just as the prism did, but this is a much more dispersive medium, so the colored light on the other side would have more room to be apart from one another. And then this light coming back to the fiber would be converged using a second lens. And so that's the idea of this design. And this is what the combinator looked like in real, because I couldn't fit the wires from the fiber, it went all the way back. But you have two input fibers here on both ends of the spectrum, close to the UV, and then here, very red, so 775 and 385. And you have the light hitting the collimating lens, and then hitting from there the transmission grating, and then from there the converging lens. And back here, at that point, there was no fiber. I was just putting a detector to see like what the shape and the profile of the light looked like. And so some results from that. This was using Zmax, so this is theoretical. The theoretical output, and because there are different scales here, sorry for that, the circles represent the same scale, so that's how you know. So the theoretical output, we ended up getting a pretty small spot width. It was 0.42 millimeters, which is something that you can imagine you can fit into a fiber. And the light throughput was about 10%, which is not the worst if you have some high-powered LEDs. In terms of the experimental output, however, we ended up getting a much wider width, and we ended up getting, well, a much lower throughput. Also sad, but not the worst, again, if you have some high-powered LEDs. But what ended up happening here, and you can see it, is there was an elongation of light, and this is because the LEDs that we were using are multi-wavelength, multi-wavelength light sources intrinsically. And so what happens is when you're trying to refract and, well, compress, but refract the light onto one output, there ends up being a stretch based on the wavelength coverage that your light emitting source is covering. And so we didn't have a great throughput at the end with this experiment, trying to fit it into a 600 micrometer diameter fiber. And we also saw that the light contribution from the red and the blue LED was heavily skewed, and that's because we had cut off from the multi-wavelength light because it was reaching a very size-limited output. just to see what would happen if we didn't have any size-limited output, well, a much larger size-limited output. I tried to just put a detector there instead, and you can see that the contribution between both sides of the spectrum is a lot more equal, and the throughput obviously is much higher. However, this just goes to show that it's really quite a difficult endeavor to be collecting an equivalent amount of light from each of the LEDs that you're using. So that was a much greater challenge. So this took us to our next design. So here we have version 2, where the combinator is the same concept, except here, rather than using fibers, we decided to use surface mount LEDs and decided to put it on a circuit board, spacing them out so that the light would align with where, the location of the peak wavelength should be based on how it refracts through the series of optical components. So that was all theoretically determined beforehand and measured out beforehand. And so everything is surface mounted here, whereas these objects are the same. We already knew that we would be losing light on the bluer and redder sides of the spectrum, but we wanted to have an experiment where we could see if it is possible to create more or less a white light flat spectrum that could be used for flat fielding, spectral flat fielding. So this is the physical circuit board. I did not make this. I worked with the technicians who made this, but these were the failed versions. This was the version that we ended up using. So you can see the different wavelengths here. They're all organized by their peak wavelength. So that's what the numbers correspond to. This is the scale. The whole setup was very small. It was very cute. So when we used it, this is what we ended up getting as our spectrum. It's quite bumpy. However, you can see that the peaks of each of the LEDs, more or less, except for a couple outliers over here, are quite in line with each other. But something else to notice here is that these peaks for each of the LEDs are quite thin. And that's because, again, when the light is going from the LED across through the optical components and finally into the fiber, when it's reaching a limited output size, the light from the two sides of the wavelength spectrum are being cut off. And so it's not that this LED, for example, did not stretch to the left and the right further. It's that the light from these ends were cut off. And so you're missing that information. But if you were to look at just the peak intensities, they do appear relatively flat, which gives a person hope that you can get white light from LEDs that is continuous to some regard. However, you have to deal with the fact that the intensity is dipping further than the full width half max in several points in the spectrum. And so just some results to wrap that up and a bit of discussion. So if we were to compare the laser-driven light source, tungsten halogen lamp, and then just a bare LED, and our ball-end setup, our surface mount setup, you can see that there is a huge difference, and we lost a ton of light. And so I would conclude that with the designs that were used in the master's thesis, that they were not sufficient enough to maximize the efficiency in which you could transfer light from an LED. It's possible that modifications to my design could be made to improve this. However, another issue that came up was just the nature of which LEDs we could find, the power of these LEDs and how much actually made its way to the end, as well as the limited spectrum of each of these LEDs. So there were quite a lot of limitations in terms of availability, in terms of design. And so it was not successful, but still a good investigation to do. I would say that possibly LEDs could become more become more useful in the future for astronomy if more market research is done for producing more powerful white light LEDs rather than us having to combine multiple multi-wavelength LEDs. So, yes, so that is that. Now, we can move on to my work here. So I have less to say about this because I started 2 months ago, and I don't really have exciting plots for the moment, but next time I do a seminar, I will. So now we're going to be looking at the upcoming Marvel array. So again, where are we now? We've seen over 5,500 exoplanets already being detected. A small fraction of these are actually characterized, and an even smaller fraction of these are sort of in the regime that many people are interested nowadays, which is about smaller than sub-Neptune, right? So very small fraction. And so what we are interested in doing here, let's do this first. So how do we actually find a planet and characterize a planet? Because characterizing is different than just detecting. This is where we start to look at a different method beyond just the RV method. We're going to look at the transit method first. So transit method, if you're not aware of it, you have an object which tends to be a star. So you have a star, and if you're trying to look, if you're trying to look for a planet indirectly via the transit method, you will observe a star photometrically, and you will notice that the luminosity of the star will dip when the planet crosses in front, and the ingress is when it starts crossing, and the egress is when it is finishing its crossing. So that's more or less the idea of the transit method. Why are we talking about that if this presentation is focused on the RV method? Well, because you can combine both of those methods to do something pretty cool. And so there's a lot of information that you can get from transits, and this is not extensive and thorough, but a lot of information you can get from the transit method, and a lot you can get from the radial velocity method. But something that's pretty interesting is by getting the orbital inclination from the transit method, as well as the minimum mass from the RV method, you can combine both of those and you can end up getting the true mass. Not just some sort of minimum mass and a lot of guesswork, but you can actually get the true mass. And from that, you can also get the density because you already have the planet's radius from transit. And from there, you can do all sorts of other cool things, like trying to figure out what the composition of the planet is from its spectroscopic data, et cetera. Really understanding like the nature of the planet system itself rather than just trying to detect a planet, right? So, because now we're in the age where we want to characterize and want to know more. So how do we do that? How do we know more? Oops, all right. Now I will introduce you to the Marvel Observatory. So the Marvel Observatory, people may have not heard of it already, have we? Yeah, we have. All right, yeah, so it's going to be located near the Mercator telescope, and the Marvel array its aim is to characterize, well, one of its aims is to characterize unique orbital architectures with 1 meter per second precision. So it's going to be located in the Canary Islands. If you have not already been to the Mercator telescope, it's here, and then it will be over here. It's a series of 4 telescopes in an array that's going to be connected to 1 spectrograph. So the idea is that we have 4 80-centimeter telescopes that will be connected to one spectrograph and then projected onto 1 CCD detector. And the idea is that these 4 robotically controlled telescopes can be looking at the same object, or they could be observing 4 different objects simultaneously. And this is excellent because we will be able to acquire up to, well, I'll put it here. We'll be able to acquire up to 20,000 measurements per year, which is pivotal if we want to be providing valuable groundwork for future space missions, as well as it being a dedicated survey instrument too. You don't have to worry so much about applying for time and then hoping that your interesting planet is going to make the list. This telescope is really focused on conducting a thorough survey of the night sky and really filling in the gaps in our knowledge when it comes to what other exoplanets are there and what are the exoplanets that are really interested for observing. And so that's another goal of Marvel. In addition, it will provide observations that can complement the future space missions of Plato and Ariel as well. And so there is that. The science cases, knowing that I'm in a large group of stellar astrophysicists and not just exoplanets and instrumentation, the science cases go beyond just exoplanets. You can also use it for stellar astrophysics as well, and we'll get there. For my work, what will MARVEL be used for? So I'm interested in the question of what MARVEL can teach us about exoplanets and star-planet architectures. Being that it's 1 meter per second precision, that means that the types of planets that we'll be able to detect most easily will be larger than Earth-like. However, it's still a very interesting parameter space nonetheless, and it's still, I would say, like worth exploring for the sake of understanding more about like planet formation, understanding, trying to understand the answer to questions of planet-star architecture evolution over time, and really answering questions such as that. Oops, wrong one. Other science cases which may be of more interest to stellar astrophysicists here. We can also use MARVEL, and will use MARVEL, for understanding better the youth and the activity of stars, star formation, volatile stellar atmospheres, understanding from that also stellar interiors as well, because all of that, of course, is related. In addition, also understanding binary systems, because before people were able to observe, exoplanets, we tended to observe a lot of stellar binary systems too. So, different science cases. Current techniques. What I'm working on now, here's just a little bit of backgrounds, because not everyone knows what a fabry-perot echelon is, but just a brief explanation. So a fabry-perot, and this will be part of my work, so it's only a little important, but it's a device that's formed from a pair of highly reflective surfaces that are partially transmissive, and they operate off of interference, where incoming light is internally reflected multiple times between mirrors, and only select wavelengths make their way out. And so the distance between these mirrors can be tuned so that we can look at specific wavelengths that come out. This is pretty useful for looking at very specific, for example, astronomical features in atmospheres and specific transitions, but this can also be really useful for wavelength calibration, because when you have all of this light coming out at periodic wavelengths, you can use that as sort of a spectral ruler. And what is wavelength calibration? So when it comes to our instrument, you observe a spectrum from the night sky, and you are trying to better understand the chemical composition of what you're looking at. Perhaps you're also looking for an exoplanet as well, but who's to say that the wavelengths that you're looking at are indeed at the number that they should be, right? Otherwise, you're misattributing them to a wrong wavelength. So it's very important, if not essential, to calibrate the wavelengths of your instrument beforehand. And so to do this, there's a multitude of ways. One of them being using a light source that has known wavelengths that are stable. Well, over time, the thorium-argon lamp will become less stable over time, but trying to use a light source that's stable with fixed wavelengths, you can use those as markers as a way to figure out whether or not you're looking at the correct wavelengths. But another way of doing that too is what I'm exploring in my current work. So I'm trying to explore a rubidium-locked fabry-perot comb. This comb here is just like I described earlier, where you have select wavelengths coming out the other end of a fabry-perot echelon, and the distance and the shape and such depends on how you fix your echelon beforehand. But before we lock this comb, it's not really particularly associated with like any specific wavelength, right? So you have to find a way to lock that ruler. And how we plan to do that is using a known hyperfine transition in the rubidium, how do I say? Like in the rubidium absorption feature, and using this at 780 nanometers as a way to lock one of the emission peaks of the fabry-perot comb, and therefore understanding better what all of the other peaks are, and using those to calibrate the spectral information that we're getting from the night sky. So that's what I'm working on now, because I've only started 2 months ago. Everything else is future work. But so for the future work that is to come, after successfully assembling this rubidium-locked echelon. We plan to implement the system into Hermes spectrograph before integrating it into Marvel. And then I'll also be working on collaborating with people here and external on a data reduction pipeline to be used with Marvel and to do an end-to-end analysis so that we can really start to process the data that Marvel is bringing in, as well as an initial science exploitation of the instruments. This would be after we're able to successfully do first light with Marvel, but really starting to collect data with Marvel and trying to use it as RV follow-up for test transit data, and trying to really see like what Marvel can do with real transit data, no longer just testing out how it works with collecting RV data. So just as a summary, early work. LEDs didn't prove super helpful for wavelength calibration, and that happened quite early on because you need quite a lot of light for wavelength calibration. But the possibility for it to be more useful in astronomy could exist in the future. And for current and future work, Marvel is brand new, up and coming, and it will have value not only for exoplanetology, but also for stellar astrophysics as well, so get ready to use it. And then prior to first light, there's a lot of ongoing work that has to do with wavelength calibration, that has to do with data reduction, and others, all of which is progressing. So that's all. Yeah, thank you.
Thanks, Mariam. While people are thinking on the questions they possibly want to ask, I personally think that actually your master thesis was quite a success. You call it unsuccessful, but I would call it a success, right? So you did an experiment, you have drawn conclusions, there you go. I would call it a success. And also, thank you very much for a very nice presentation of your future work on Marvel and Marvel as well, because I think that's something that some people in this institute might have been missing so far, actually. Questions? We have plenty of time. So I start with Luke here, then go to Bart, and then whoever else wants to ask a question.
Yeah, thank you for a nice presentation. You mentioned very briefly the white light LEDs, and I was wondering actually how would they fit in this? Like, I can imagine they could do all you wanted in one go, sort of.
Yeah, so white LEDs exist, and they were actually part of my second design. They're actually part of my second design. I have a warm white LED here and then a cool white LED over here. So white LEDs appear white to the human eye based on two different styles of mechanisms. One is using RGB, so the white light will have a combination of a peak in the red, the green, and the blue. And then another style is that it will peak in the blue, but it will have like a phosphor coating on top of the LED, and the coating will absorb the light and then re-emit at redder wavelengths. And so that's how they appear white to us. However, if you're trying to use one of those mechanisms to create a perfectly flat, continuous white light spectrum, it doesn't work, because as soon as you measure it with a spectrometer, you see that there's like 3 peaks, or there's just like 1 peak and a small hill, and so that wouldn't really work for our purpose because we want it to be flat. Yep.
Although I have seen white light LEDs with the phosphor layers that actually have a very, very broad like phosphor re-emission peak, say, and very, very tiny blue end. So I think there's room for that.
Yeah, I think there can be, and I think like a possible solution is maybe using one of those, and then maybe using a collection of a couple or a few other wave LEDs that would fill in the gap, because the profile tends to look like this.
Yeah.
And if you could fill in this gap here, sorry guys, if you could fill in that gap sort of in the middle, that would be great. However, another downside of white LEDs is you have the power that you have in that LED, but spread over the full wavelength spectrum that you're trying to cover. And so even if you could cover the spectrum, it's not very powerful once you get it out to the output. So, yeah. It's a bummer.
Thank you.
Yeah.
It's wonderful to see how precise the engineering plotting can be. Bart.
Janis had a question first.
Young people first. Thanks for the presentation. It was very clear, and a lot of it is very familiar to me. I have two small questions. One is a naive one, and the other one is, I'll tell you in a second. The first question is, you said that the throughput of the tungsten lamp was dropping at 400 nanometers, and that's one of the issues that you want to use LEDs for. So why not just use what exists already that covers the white light quite nicely, and then supplement that with a source or an LED of your interest in that small region where it kind of drops very dramatically? Is that something that was considered? Is that even possible? Like, yeah.
So we didn't consider doing that because we were looking at just using one method and seeing how well that worked on its own. I think if we were to try to do that, I don't know how easy it would be because the emitting surface of the cathode ray lamp is already larger. So I imagine there would end up being cut off from the LED light, but I'm not sure how well it would work, to be honest. I mean, that is something to think about. That is a possibility.
I was thinking if the problem is there,
For sure.
So the second question I have, there was a former master student, we did our master together, Gabriela Renamuro, who worked on the very specific rubidium line that you're using. So she spent a lot of time studying that. And I do recommend you read your thesis. I can put her in, put you in contact with her.
That would be
if
great.
You want. One issue that we both faced, me for a different reason, is that the spacing between the ethanol lines, even though theoretically it should be equidistant, can be affected by a lot of factors. I don't want to get into technical here. So the rubidium line will lock you on a specific line. However, this theoretical expectation that the other ones, the other peaks are equidistant, is not so obvious to me. So how do you plan to kind of address that? If I just put it very basic.
I had a small discussion about that. The idea, and you're absolutely right, once you kind of get to the other ends, it's a little bit less certain. The idea would be to not only use the rubidium line, but also to have a second wavelength marker as like a second marker within the spectral ruler. So at least you can use both of those as a way of trying to lock the whole comb. But as for going all the way to the ends of the comb for the visual wavelength regime, I think you just have to rely on the two markers in the middle. Yeah.
Okay, I'll be very curious for your next seminar.
I'll let you know.
Thank you so much. All right.
Yeah, I have a comment and a question.
Okay.
The comment is addressing the generation of astronomers who were born around the time of the first discovery of an exoplanet. The green thing behind you is called a blackboard, and you can actually
I forgot I had chalk. I was too nervous.
I know. It's but yeah, okay.
Sorry.
It's even in the times of PowerPoint presentations. It's useful from time to time.
No, you're absolutely right.
Now, my question. If I look in the Torlab's catalog, I find fiber combiners where you just the opposite of a spliced fiber, where you bring three fibers that are just merged into one, and they have an efficiency of 94%. Wouldn't that be an easier solution? Or is there a reason not to do that?
An easier solution than using
But you
separate
couple on three
fiber
fibers, you couple an LED, then you use, and you can even cascade them, because with 94%, it's quite efficient.
We didn't consider using fiber combiners. I think we were trying to keep it low cost, so I'm not sure how much a fiber combiner would cost. But another idea that we had that I just didn't have time for implementing was like you take the light and couple it into the fibers, but towards the end you remove the cladding from the fibers. So that way, instead of having them all have to be so spaced, you can get them closer together. And so I guess that would be like my fiber combiner, but that would be the cheapest way of doing it. I just didn't have time to do it by the end of the project, but I'm not sure.
But now you're in the phase of your life where you don't only have to think about cheap, but
it's
also important. But maybe also an option to consider. We have a lab here where we can write waveguides ourselves. Maybe a clever compact device combining with waveguides 20 LEDs, we could maybe make a nice product that everybody would like a lot. I don't know. It's quite efficient, I think.
Maybe.
Just a small answer to the fiber combiner. If you combine two fibers, they only get 50% of the flux in each of the fibers.
Oh.
So each time you combine them, you drop it by 50%. So
Why do the Torlabs claim it's 94%?
There is a cool discussion ongoing, and a perfect topic for coffee discussion, guys.
Yeah, also to bounce on that, but I think there's also like photonics lanterns that could accomplish this, like merging these lights if we take them like the other way around. Also to bounce on Luke's comment and this idea of white lights and trying to combine white things with other parts of the spectrum. The problem is also when you start going into a problem where an approach where you use an inverse spectrograph to combine the light, then if you put a white source in there, it's going to be spread across at the other side of your thing. So once you select this approach, you're kind of bound to having narrow bands input sources, right? But so that's actually why I wanted to ask whether you considered another way to couple several sources into a single fiber by using more an approach of separating, like having several pupils or subpupils inside your focuser or your injecting lens, instead of trying to de-disperse the thing. So kind of a more parallel design, having like instead of using a grating, have instead micro lenses in front of your of each LED, and then having a larger lens to inject. Is that something that you considered? Is it not actually as efficient as it could sound?
When you say subpupil, so the micro lens I think that you're describing was similar to what we did with the ball lenses. It was just another way to refract the light to get it better onto the collimating lens. But when you say subpupils, do you mean more like, rather than injecting it through some sort of mechanism, more like the integrating sphere where you would just have the light be there? Or?
No, I'd say use micro lenses to have collimation, to collimate each light source, and then have a large, have these pupils be part of at different places of the larger pupil for the injection.
Yeah. So you would still end up having an extension of light at the output anyway. Okay, now I'll use this. All right. Oh, I have different colors. That's exciting. All right. All right. So if you had like let's say like one subpupil and then another, and then you were able to collimate them, let's just say as such, and then here you have the rest of the system. Even if you were to perfectly collimate them, what ends up happening is if you were to run through the system from the white light all the way to the light that would be spread out over here, the light from the two extents of this red LED, it's not the same wavelength, right? And so you would end up really having red light that looks more like this. And so this limited light that's a large wavelength range would still end up being spread when it goes back through the system the other way around.
Not if you're considering, like, I mean, in this approach, those lenses would be achromatic, so you wouldn't be dispersing this stuff.
No, what I'm saying is, if this light was only one wavelength, let's say like 770 nanometers, and you were able to collimate it onto the lens, you would able to focus it onto the fiber just fine. However, because what the actual extent of the wavelengths is more like 760 to 780, nanometers with a peak at 770. The light from going from white light to red would be more spread out. The refraction angles would end up being different for the two extents of the wavelength range. So if you were to collimate it and then have it hit as more of a straight line, but representing a range of wavelengths, it wouldn't be at one point when it got to the end. Sorry. Okay.
Yeah, it sounds like you can guys follow up on this a bit later. So Bart, maybe to bounce back to this neat thing as a blackboard, would you also suggest a binocular for same generation that you were referring to?
Hi, Mariam. Thanks for this
Hello.
nice talk. I want to go a bit to the future of the Marvel survey instead. So, you know, from for the Marvel team, there's also the ultra high resolution mode. Is there anything you'll be working on there as well? Because I'm thinking a bit about like what is the precision we can actually do for, you say 1 meters per second, but is that actually what is the ranges that you're kind of expecting to see with the fabry-perot echelon now? You're gonna use that.
So, sorry, you mentioned something I completely forgot to mention. So there are two different resolution modes. There's, I forget the exact name of it, but the more of the standard resolution mode, that's, I believe, 90,000, and then the ultra-high resolution mode, which is 150,000. Someone can disagree with me if I got the number wrong. But I believe that the goal in getting to the 1 meter per second, I would say this would be like the limit of what we're trying to reach. Could you repeat part of that question again?
No,
Sorry.
I'm just curious, like, what your thoughts about like these two different like spectral resolving powers, because like what kind of like persistent are we actually expecting? I mean, we always say 1 meters per second, but let's be honest, that's really like the limit, right?
Yeah.
Probably for Mercator. So I'm just curious, like, what is kind of the range that you expecting like to see, and have you looked at any spectra so far that maybe will give you any indication of what we can reach with?
I haven't looked at spectra myself yet.
Okay.
For trying to, like, I say, contend Marvel's expectation with what we would be able to see in terms of spectra. I guess like what you can imagine being able to observe is with like the ultra high resolution mode, you're able to look at fainter stars that you wouldn't normally be able to see with the standard resolution mode. And if you were to take all 4 telescopes and focus them onto the same object, but otherwise, I think if you're using like the standard resolution mode, you should be able to see more or less like the larger planets, like super Earth, mini Neptune type of planets. I'm not sure if that's answering your question or not, but
I mean, I don't know. So
yeah.
I'm just
Yeah.
curious. Like also in comparison to the echelon, like if you use just a normal foreign argon lamp, like is that like a huge difference? I guess like that's the reason we want to go there, right?
Yeah.
So is it like from 100 meters per second to 1 meter per second? Is that?
So thorium argon is actually pretty great. However, its quality kind of deteriorates over time, and so what we're looking for is more of a long-term solution that could be left just stably on its own for very long periods, limited maintenance, because the idea is to have a robotically controlled observatory, so you don't want to have somebody consistently recalibrating every evening. That is the problem, I believe, with HARPS, who's using the thorium argon lamp, but they have to recalibrate every evening, which is not great. And so we're looking for more of like a long-term stable solution. So that's the difference here.
Okay, thanks.
Yep.
Real quick remark, I think, for people, and Mariam can correct me if I'm wrong, but when you refer to 1 meter per second precision, you mean at the level of the instrument stability. You don't mean that it's going to be 1 meter per second accuracy when you take into account the activity of stars and stuff like that, correct?
Yes. Yes. That's true. Yes.
So yeah, I'm not an instrumentation person, but how I thought of it working with the echelon was that you need something to lock the echelon on each order. Is that true, or am I completely false? You only need it on one of the orders, because I imagine the Marvel output being like a bunch of lines on your CCD, and if you lock it at one of the orders, it's not necessarily locked on the other, or is that not necessary?
No, I think it's not order dependent, but if an expert in the crowd wants to correct me, they can, but I believe you can just correct it at one or more wavelengths, because as Yannis said, towards the ends of the spectrum, it gets a little shoddy. But
Okay,
yeah.
so misunderstood. And I have a small second question that really links to what I think Nick was trying to get at. If we, at one point you said that you wanted to get the echelon also in the Mercator, the existing Mercator setup. Are we expecting like a huge upgrade in our Mercator possibilities then, or is that about to stay the same and it's just like a ease of use kind of thing?
I think it should also be an upgrade too.
Okay.
Yes, because I'm less familiar with the instrument, but I believe it is an upgrade for the Hermes spectrograph. So improvements and stability.
Thank you. Very nice talk. Do you happen to know if LEDs are aging sensitive or temperature sensitive as for a tungsten lamp?
They are temperature sensitive if you apply like too much like voltage, for example, like to the LEDs. You can reduce the lifetime. Unfortunately, that's something that I did at some point in my experiments. So you had to switch out the LED. But and lifetime. So the experiments that we did didn't really test them to their full capability of the order of 10,000 hours. Unfortunately. I would say the red LED that we had, let's see, where, okay. The red LED that we had that was over here, there's actually also an LED here, but it was so low power to begin with that you couldn't even tell it was there. But the red LED that we had was originally like higher power, and this is on the surface mount technology, the circuit board. But I think maybe an encounter with a little bit too much heat lowered the life of that. But over the course of several hours, I would say maybe like up to 50 or so hours. Everything else stayed relatively the same, but I didn't do any really extensive stability checks because this was very, very much towards the end of the project. So only the red was affected.
Okay, thanks.
Mm-hmm.
All right. Sorry, Alex. With all the respect to Mariam and people in the room, some portion of the respect goes to the lunch hour. So I'm going to have to cut here. Thank you guys all. Thank you, Mariam, again for your very nice talk. I encourage you to continue discussions during or after lunch, and see you next time.